So this is the first in a series of 5 webinars that we're running on the subject of large language models and their applications in bioinformatics. So this is obviously a really hot topic, really exciting area to be working in, and we've got some really nice speakers lined up. So we've got 4 really cool talks about really cool projects. So um, developing a data set for an LLM project is the first up, which I think is next week. Melanie Volmar will be talking on that. That's a really important thing to get right for your project. And then we've got Matthias Bloom from Interpro to talk about using LLMs to generate protein classification summaries. And then a real treat, we've got the developer of BioChatter, Sebastian Lobentanzer, to talk about that framework and using it to drive LLM-driven bioscience forwards. And then finally, we've got a really hot off the press webinar from Cancer Models talking about using LLMs to extract domain specific information from scientific texts. So the webinar today is foundations, basics. So we're going to start from the absolute beginning. So this is intended to take you all the way from the transformer model up to an LLM and then have a look at some of the techniques that are used to train them and some ideas for how we can actually use them and get them to do useful things. So we're going to look at what a transformer actually is. So starting from the very beginning with the architecture as described in the original paper. Then we'll look at the GPT architecture and how that's different and how the use of pre-training really powers this. We'll look through tokenization, which is a really important thing to understand, and then go on to look at how we go from a foundation model to an assistant and how we train that assistant to be useful. And then we'll get to some more kind of practical aspects of how you use LLM. So getting your data in, how you prompt them, some ideas for ways to approach that problem. And then something which is often overlooked and a bit transparent to users, but incredibly important is decoding and getting data back out. And then finally, we'll touch on hallucinations and how you can potentially mitigate them in some cases. So, way back in 2017, which feels like a long time ago now, a team that was primarily led by Google Brain put out this paper that said, attention is all you need. And what they showed was that a particular combination of what they called multi-head self-attention with cross-attention was a really good model for their particular problem. And the problem they were trying to solve was machine translation. And this is what powers Google Translate in the background, but it's actually a really tricky problem. So if you look at this example at the bottom here, we're translating a sentence in English to a sentence in Japanese. And there is not a one-to-one relationship between words. There's not a one-to-one kind of mapping between locations in the sentence and things. Context really matters. The meaning of a word depends on context. And this is actually really quite hard. And what this team realized from doing translations themselves was that they encode the meaning of the source language before decoding it into the target language. And that's what they based their architecture on. So the original transformer had 6 encoder layers and 6 decoder layers. There were some other little bells and whistles like positional encoding and the cross attention thing that I mentioned, but this was the basic guts of it. And when I talk about a layer here, what I mean is a self-attention mechanism and a feed-forward neural network. So a feed-forward neural network is just a standard fully connected neural network. And the self-attention is where the magic really happens. So if we think about how, as a human, we would understand a sentence, what would happen is we'd read something and pay particular attention to some words in it. So we don't have to hold the whole thing in our kind of head at once. We can look at individual words and from context work out what they mean. So if we look at the word capital, I can think of at least 3 meanings of the word capital depending on the context in which it's used. It could be a city, it could be a letter, it could be punishment, it could be money, it could be any number of things. And self-attention attempts to capture this fact. It's a mathematical tool to capture the fact that the meaning of a word is dependent on the context in which it's used. So what happens is each word tries to work out how much attention it needs to pay to each other word. And this is done with 3 matrices, the Q, K, and V matrix. And so this down at the bottom here is the first of 2 equations that are in this talk. And it's not it's not that bad. So I'll walk through it. So the Q matrix encodes what the word that we're on wants to know about other words. So it's trying to work out what its context is. The K matrix offers up the identifying features of each token, what makes it relevant to everyone else. And the V matrix contains the kind of semantic meaning of the token. So what this little animation over here is trying to show is that each word in this case reaches out to each other word with its Q matrix, multiplies it with that word's K matrix to get an amount of attention that it should pay to the V matrix of that word. And putting all that together, we get this thing up here, which is an attention matrix. So this isn't real, but if we look at, for example, in the sentence, the capital of France is Paris, the word capital is going to, the meaning of it is going to depend on how it relates to other words in the sentence. So it's going to pay a lot of attention to France and Paris because that means we're talking about a capital city. And in this way, the self-attention matrix captures language really well. So it captures things like subject-verb relationships, article-noun dependence. It can capture negation and all the things that we want to model in a language model. So this is the real core key thing that is driving everything that LLMs are able to do. So I said that the original transformer had encoders and decoders, but what about the GPT architecture, which is what kind of everything that went really big is starting to use? So in 2018, so the paper came out in 2017 and no one really realized what a big deal it was until in 2018, OpenAI thought, what happens if we just take the decoder of that transformer and then see what we can do with that? Well, if you do that, you have a purely generative model. And what they decided to try was creating a model that can just predict the next word. So you feed it some words and it predicts the next one. And what it actually predicts are called tokens, which we'll come on to in a minute. But this is effectively just autocomplete. And this type of model is something called autoregressive. So what that means is you generate a word, and then to generate the next one, you feed the output back into the input and generate the next one. And you build up that generation kind of word by word or token by token. Well, what that means for training is that you can take a sentence of, say, 10 words and chop it up into 10 training examples, and you can train in parallel really fast. And this is one of the really big advantages of the transformer architecture. But there's a key modification that we have to make in that self-attention matrix, and that is to stop it looking at the future. So this turns the attention mechanism into a causal attention mechanism, where it's only allowed to look at things that have come in the past. So here is an example where we've got that sentence again, the capital of France is, and we're trying to predict what should go in this last space down here. In order to do that prediction, we're only allowing words to look at things that, came before them in the sentence. So the can only look at itself, capital can only look at itself and the, and so on. And by doing this, we hope that this conditions the model to produce the word Paris here. That would be a good completion. And what you see from a causal attention matrix is this characteristic lower left triangular shape. So in green are the things it's allowed to look at, and in red are the things it's not. We're basically stopping it from being able to look into the future to predict what's coming next. That's all it is. And this turns our kind of standard transformer into something called a causal language model, something that follows causality in generating text. And so GPT-1, which came out in 2018, used about 600 million tokens. So that's about 800 million words, to just kind of give you a number to hang some later comparisons off. And one of the interesting things that I found when reading the original paper was that GPT-1 wasn't really particularly used to do completions. So what they aimed to do was use this generative pre-training technique to make a model that understands language and then fine-tune it to do other things, like named entity recognition or sentiment analysis and that sort of thing, in the same way that we use smaller models now like BERT. But GPT-1, with this 600 million tokens, and it was 117 million parameters was the start of this introduction of really powerful pre-training on large text corpora. And 2018 was a kind of time in machine learning in general where this idea of pre-training on really big data sets was a really big thing. So at the time I was working in computer vision, and we were pre-training things on natural images, images that you can take on your phone, and then doing a technique called transfer learning to apply them in medical images. And this worked really well because the models learnt the structure of images. This is exactly the same thing, but in language. So the model learns general language patterns before you then fine tune it on a specific task. And then a couple of years later, GPT-2 came out, and GPT-2 was 1.5 billion parameters. So we've gone from 100 million to a billion in a year or so. And when GPT-2 came out, the OpenAI started to get a little bit cagey with releasing it because it was really convincing at writing completions. So they found that you could condition the model on a prompt. So you can feed in this bit of text at the top, which kind of reads a bit like the start of a press release about a scientist discovering unicorns in a remote Andean valley in the Andes somewhere. And then GPT-2 can continue this with what looks like plausible text that a journalist might write about this completely fabricated thing. So OpenAI recognized the potential for misuse of this and were very cagey about releasing the model. They released various checkpoints of various sizes slowly so that they could monitor how it was misused. But this was the start of something magical, something where we can feed in text and get the model to do something. And then GPT-3 came out and was even better. So GPT-1 was 100 million, GPT-2 was a billion, GPT-3 was 175 billion parameters. It's absolutely huge. And this was where they first demonstrated few-shot learning and in-context learning. So here's an extract from the appendix of the GPT-3 paper where they feed in some titles and names of poets and the poem text, and then they make up a title, feed it a real poet's name, and it generates a poem in the style of that poet. And this is in-context learning, which is incredibly powerful and kind of paved the way for a lot of what we do now. And so this should give you an idea of scaling and the importance of scaling. So all that happened to make large language models into large language models was we took a standard size language model. So the BERT that you would use today is only 100 million parameters probably. And we just ramped up the size until it was huge. And then it started to have this emergent capability to do things. So I mentioned tokens as a number of things that GPT-1 was trained on, but what actually is a token? Well, we saw the self-attention equation, and that was full of matrices. So all these things are doing really is lots and lots of matrix multiplication, and that works on numbers, not text. So we need a way to convert text that humans read into numbers that machines can read. And we can think of a few ways to do this. We could, if we only want a model that speaks English, we could just take the English dictionary and number every word in the English dictionary from 1 to 600,000 or however many there are, and say, right, this is how we convert words to numbers. But what if we then want to translate into French? We then have to go get the French dictionary and add that. What about if we want to translate into German, where we have compound words? That's going to really mess with this system. So this just is a complete non-starter. This isn't how it works. So what we do instead is we observe that lots of words have similar patterns of letters. So I've chosen 3 here that have the CH pattern in them. And we basically base a system off this. So I think it was around 1994, this technique called byte pair encoding was released as a way to compress text. And what it does is it starts with letters. So we seed our tokens with just letters that we might want to use. And then we take a really big corpus of text and we look at the frequencies of pairs of letters. And that forms our first round of tokens. So from this, we would look at our corpus of 3 words and say, the pair of letters CH occurs 3 times. So I'm going to make a token that is CH. And then we iterate again with all the letters that we had last time, but whatever new tokens we've created. And we say, we might say this time, well, CHI occurs twice. So I'm going to make my next token is going to be CHI. And then we do it again. And we keep doing this iteratively, merging pairs of tokens together until we hit a vocabulary size that we want. Vocabulary sizes range from the sort of tens of thousands up to a couple of 100,000. So GPT-4's tokenizer has a vocabulary of 200,000 tokens, so 200,000 different little chunks. So what do these things look like? Well, here is the text of the description of EMBL-EBI taken from our website. So this is a fairly bog standard little bit of text that is not particularly remarkable. And this is how a tokenizer would see it. So every colored block here is a token, and it's just intended to show you where the token boundaries are. So the colors don't mean anything. They're just there to help with visualization. So purple doesn't correspond to purple in any way. And this is how the model actually operates on that text. So there's a couple of interesting things with this. So there's 470 characters in this, and it gets compressed into 92 tokens. So that's quite a decent compression ratio. And the other interesting thing is the tokenization of the acronym EMBL. So EMBL here at the start is tokenized one way, and here in the middle is tokenized completely differently. And that's because there's a space before the E. That happens frequently enough that it's a token in its own right. And this can cause some interesting problems, which we'll come on to in a minute. But what the model sees is this. So each one of those 200,000 tokens has an ID associated with it, which is the number that gets fed into the model. And then the model is trained to know what to do with all of these numbers. And just to highlight, these are the two ways that EMBL is represented by this tokenizer, which are very different. So I've kind of alluded to this, but tokenization is an interesting thing in that it can introduce some problems that you might not immediately think about. And one example of this that's become a bit of a meme at the moment is counting the number of letters in a word. And the classic is counting the number of R's in the word strawberry. So if I run the word strawberry through that same tokenizer that ChatGPT uses, you see it breaks into 3 tokens, 2 of which have got R's in. But the model doesn't necessarily know anything about these tokens at a finer resolution than the token itself. So it will have a kind of semantic understanding of what a berry is, but it might not know that the word berry has 2 R's in necessarily. So that's why this seemingly very simple question is actually quite hard for some LLMs to deal with. The same sort of thing can be applied to numbers. So if you have long numbers, they will almost certainly be tokenized into multiple tokens, and then comparing 2 big numbers becomes basically impossible for the LLM. Order of magnitude comparison becomes really difficult. And we also end up with meaningless units. So the word unspeakable has a very specific meaning, but unspeak and able might not necessarily capture that. And you can say, well, isn't this what the attention mechanism is supposed to be doing? And yes, it will. But we're loading more and more responsibilities onto that mechanism. So it's got to keep track of the fact that these 3 tokens go together and mean one thing. And I then need to query everything else with all 3 of these tokens, really. And at some point, the model's capacity to just handle all of that stuff will start to break down. More relevantly to bioinformatics, maybe, is that we have lots of gene names and things which we are probably quite familiar with, we use a lot, but aren't sufficiently frequent in the LLM training data that they're a token in their own right. So the example that I've got here comes from a paper about long non-coding RNAs in a disease called CAVD. And I ran it through the tokenizer, and what we see is that terminology gets broken up. So the terminology for long non-coding RNA, LNC-RNA, is broken into 4 tokens. And all of the IDs get broken into multiple tokens. So anything that has to reason over these entities has to implicitly reason over multiple tokens at the same time, which can lead to things not working as well as you might expect. So that's tokenization. And so now we've got the kind of idea of how a transformer works, what self-attention is doing, how that maps onto tokens and kind of the interplay between tokens and how that can sometimes be a bit difficult. And we know that if we throw enough data and enough compute power and enough time at this model architecture, we can get something that can predict the next token with a high degree of accuracy. And that thing can then produce plausible sounding text, but it's not actually that useful. So at the moment, we've got a very expensive, fancy autocorrect. And that's what a foundation model is. So a foundation model has been trained to predict the next token, and that's it. So they're really good at that, but they don't naturally follow instructions, which is what we want. So we want a model that we can say, write me a piece of Python code that does this, and it will understand that what you want and then do the thing. So there are a few ways that we go from this kind of autocomplete to an assistant. And the first step along the way is something called supervised fine tuning, which, if you've done any amount of machine learning, you'll probably have come across this. But basically, it's where we take the foundation model and we fine tune on top of it with a set of input output pairs that describe the thing that we want it to do. And this can be any input output. You can get it to do named entity recognition with this as well. And that supervised fine tuning process transforms the raw prediction ability into something a bit more useful as an assistant. And it's also, so it's the starting point for more powerful techniques, but it's also where the model first learns to speak in the first person and where it gets its first taste of saying no. So if we compare a couple of models, this is Gemma 7 billion, the foundation model, and I prompt it with just who are you? It then completes, and what the completion is what you see in blue. So it finishes off with a question mark for me, and then it produces some text that it thinks is a likely continuation of this question. It doesn't answer the question. If you compare it to the instruction tuned model, you can ask that, who are you? And it will tell you who it is. It says, I am Gemma. I'm an open weights AI assistant. And then it goes on at length to tell you what it can do and what it's been trained for. Compare a slightly more interesting example. So this is an example of a refusal that is trained in by the fine tuning. So I can prompt the foundation model with the meaning of life, the universe, and everything is, and get the expected answer of 42. And then the model will go on to kind of riff on the theme of some Douglas Adams things. But if I ask the same question to the instruction tuned variant, it will say no. As a large language model, I don't have the capacity to comprehend such profound questions, and I refuse to answer the question. And so this is where that sort of behavior is baked into the models that we use. And I said supervised fine tuning is just the start. So this is to take it from something that just predicts the next word to something that can kind of follow instructions. And then we go and run some really more powerful techniques on top of that to get the models that we're used to using. So the one that we're going to cover in a little bit of detail is reinforcement learning from human feedback. But you can also do reinforcement learning from AI feedback. So this is the kind of thing that made AlphaGo really good, where it played against itself. You can do something similar with LLMs. And reinforcement learning from verifiable rewards is where you have a definite, the LLM either got the question right or wrong, and you can use that to provide your reward signal. And that's the kind of reinforcement learning that was used to give us DeepSeek R1. So that is a very simple reward scheme, but it's incredibly powerful if you've got enough compute to make it work. So reinforcement learning from human feedback. Well, first of all, what's reinforcement learning? So supervised fine tuning is where we have the input and the expected output, and we can force the model to produce the expected output. We can measure the error. How many tokens did it get wrong? And back propagate that through the model to update all the weights on the way and make it more likely that it'll produce that output the next time. This is really precise and gives the model very clear direction in which it needs to go. But Supervised fine tuning to get a model that's good enough would essentially require somebody to pretend to be an LLM and answer tens of thousands of user queries as if they were the LLM. So this is really expensive and really time consuming and not efficient. It's not good use of human time. So instead, we use a technique that's been around for ages called reinforcement learning, where rather than having this exact predicted output and then propagating the error through, we instead have a reward function and we try to optimize the reward instead. So with reinforcement learning, the model learns from feedback on its outputs, and this is way easier and cheaper to collect, and it means that we can more efficiently use human time to just rate things or compare things. So the specific technique that gave us things like ChatGPT is a technique called proximal policy optimization, which is way over beyond the scope of this webinar, but just to give you something to Google afterwards if you want to go and have a look at this. Basically, this schematic shows what happens. So we take a library of prompts. These are things that we want the model to handle. We feed them to the LM and it generates a bunch of generations. For each prompt, we generate 2 or maybe more generations. We then get a human to say, we ask the human, of A and B, which do you prefer? And the humans rate a couple of thousand examples like this. We then train with supervised learning a reward model that is trying to reproduce the human preference, basically. And then we run it through this loop where the LLM generates pairs of outputs. For example, the reward model says, I prefer A or I prefer B. And that signal is fed back to the LLM, and the LLM gradually moves towards the preferred output. There's a couple of problems with this. So the reward model can be tricky to train. You need a fairly large amount of preference data to train one, and then it's very susceptible to what's called reward hacking. So the LLM can produce outputs that give it a really good reward, but aren't what we actually want. If it can find a way to cheat and game the system, it will, because that's the lowest effort way to get a high reward. That's what we're optimizing for. So there are more modern techniques that kind of do away with some parts. And the main one to be aware of is direct preference optimization. So in direct preference optimization, we don't bother with a reward model. We just generate, so everything else is the same. We have human rated pairs of things, and then we try to produce a reward signal based on the sequence of tokens being more likely in the preferred generation than the dispreferred generation. So there's no reward model in DPO, and that means that it's not as susceptible to reward hacking. It's a very clever technique, and the mathematics kind of shakes out in such a way that they are almost equivalent, and in some cases DPO is better, and in other cases RLHF is. But that's the kind of current state of the art, I think. And if you want to read the original papers on this, I've put the links in there. And Hugging Face has really good documentation on it if you want to go and kind of learn how it's done in real life almost. So that's more or less the end of the deep theory section. So now we're going to go on to some more practical things and working with LLMs and things to consider when you're working with LLMs. So I think I mentioned at the start, we're almost certainly going to need to be getting data into an LLM. So the LLM has a given window that it can work with. So it has a number of tokens that it can pay attention to at a time. That's called the context. And getting data into that context and then prompting the LLM to do stuff to it is basically the rest of this talk. So there are a few ways that we can get data in. The simplest is to not bother. So if whatever you're asking about has been seen by the LLM in its training data enough, you can probably pull it out of that training data quite easily. This can be seriously risky, though. So there was a case in 2023 where a US lawyer got in big trouble because they used ChatGPT to do his case research and cited non-existent cases to a judge. And there's a paper which I'm going to mention in a bit when we talk about hallucinations that estimates that 70% of fact-seeking generations from Llama 2 contained hallucinations, just straight made-up stuff. And for GPT 3.5, which is what runs ChatGPT, at probably not now, but a while ago, that was 60%. So these hallucinations are absolutely everywhere. And this is probably a really, really bad idea. Please don't do it. So the next level of effort is to actually put something in for the LLM to work on. And this is kind of where we're probably all going to be starting from. So I call this context stuffing, but there's other names for it. But what you basically do is just put stuff in the context. So this could be, I want to know something about the protein in this paper. Here's the paper, ask the LLM a question. And this works most of the time, but if you think about it, the signal to noise ratio is terrible. The actual bit of the paper that contains the interesting information is a tiny subset of the whole thing. But the reason this works is that these models are really good at recalling things from their context. But you also run into this thing called lost in the middle, which you probe with a benchmark called needle in a haystack. So this guy, Greg Camarant, I think, came up with this idea of taking text and just sticking loads of text together and then putting a sentence somewhere in it and seeing if the model can recall what's mentioned in that sentence. So the haystack, all the text that doesn't contain the answer, is Paul Graham essays. And the needle is a sentence that says the best thing to do in San Francisco is go to Dolores Park and eat a sandwich on a sunny day. And then what you do is you build up this huge context with all of this distracting text, and you put that needle somewhere in the middle of it, and you see if the LLM can answer the question, what's the best thing to do in San Francisco? And what he found with this is the original version of GPT-4 was that there's little islands where suddenly the model just seems to have a complete blind spot to any information that's in that region. And I should point out that this benchmark now is green pretty much completely across the board. The labs have picked up on this and optimized to it, so this is not foolproof anymore. And so from that, you would think, well, maybe I can just throw 10 papers in and it will be fine. It can answer from all that. But there's a recent paper that kind of implies that this isn't as solved as we thought. So when you think about the sentence, the best thing to do in San Francisco is, and the question, what's the best thing to do in San Francisco? Those two things have a lot of literal match overlap. So San Francisco is mentioned the same and other things. But as soon as you make your needle not have literal matching in, which is what the whole point of this paper is, and I recommend going and reading it, suddenly the model can't do this very well over very much context. So it's yes, it's true that you can throw 100 papers into Gemini 1.5 Pro, but you probably won't be able to effectively use all of that context. So it's something to bear in mind. So how can we do better? And one way is to improve that signal to noise ratio. And one technique for that is retrieval-augmented generation. So in this, we could fill a whole webinar with just this, but basically what you do is you take your set of documents, and you chop them up, and you embed those with a model into vectors. And then when a user wants to know something, you can make a vector similarity query against your big pile of vectors that you made and pull out only those bits of text which match the query somehow. And that means that you end up with much less stuff in the context that's much more relevant, but it needs all this pre-processing and it needs all of this kind of infrastructure around it to make it work. And there are several key points in this where the choice of what to do is really not clear. And there's some work on it, but it's still kind of a bit of an art to get this thing to work properly. So what's the generalization of this? What's the kind of logical endpoint if you take this to the extreme? And that is where we're heading now. So the current really hot topic with LLMs is agents and giving LLMs agency. So what this means is we have the LLM sit in the driving seat and we tell it, here are a bunch of things you can do. Go and figure out how to solve the problem. And the things that they can do come as tools. So a tool is, you can think of it as a function in Python or something with a description of what it does. And the LLM can read the description and choose to use it when it needs to. And a retrieval-augmented generation query to a system like this could be one such tool. But other tools could be go and search Google or DuckDuckGo or whatever. Go and search Wikipedia, pull back the summary for a page that matches this string query, or try and compile this piece of code, tell me why it doesn't work, and things like that. And the key difference with this is that the LLM can actually choose when to use a tool. So it only gets the context into its kind of window when it's absolutely necessary. And the context that it gets is really relevant to what it's doing right now. So there's a couple of resources here. Down at the bottom, the top paper is the paper that introduced RAG, and there's a really nice write-up of it on Wikipedia, which is where I got this diagram from. And if you're interested in agents, Hugging Face are right now running a course on how to write and develop agents in their library called Small Agents, which is really, really good. And I highly recommend following along with that, even if you just do the introductory unit of it that tells you in real depth what an agent is and how they work. That would, if you're interested, that would be a really good thing to go and do. So now we've got our data in the context window of the LLM. We need to get the LLM to do stuff to it. And this is where we get into the kind of art and science of prompting and prompt engineering. And I like to think of prompt engineering as a kind of hierarchy of effort. So the lowest effort thing you can possibly do is called zero shot, where all you do is you give the LLM the text and you just ask it to do something. So that's what this first step of this animation is. What mRNA, microRNA interactions are in the above text? Give me some JSON that's got it in. Don't do that, basically, at this point. The thing that you can add with minimal effort that improves model performance by quite a long way is just the sentence, think carefully, step by step, before you answer. That triggers models oftentimes to start what's called a chain of thought reasoning. So it will walk through what it's thinking step by step before it answers, and that guides it towards better answer a lot of the time. And then we remember that these models are really good at in-context learning, and we can try something called few shot. So this is where you give it one or two examples. So in this case, for example, if you see this binds to that, you should output this piece of JSON. And then you combine the two and you have few shot chain of thought. And then you're starting to get to quite a lengthy prompt, but probably more powerful. And this goes back to one of the key realizations recently with LLMs is that it's really important to let them think. So the chain of thought idea came out quite a while ago now, but it's come back into vogue now with reasoning models. So the O series from OpenAI, O1 and O3, do exactly this. And DeepSeek R1 is a reasoning model. So it generates this chain of thought before it tries to answer. And just as an example, I asked a distilled version of DeepSeek R1 to count the R's in strawberry, and it got the right answer, which is pretty good for an LLM. But note that it took nearly a minute and a half to count the number of R's in strawberry. And the reason for that is that it has a really verbose reasoning style. So it has a real crisis about what strawberry means and whether it matters that there's straw and berry and how many R's are there and can I even count and what's going on for a minute and a half nearly. So there's a kind of trade-off of, yes, you can get the right answer, but you have to burn a lot of CPU time to get there, thinking things which are not necessarily that useful. But people like this sort of style, and using R1 especially to generate a chain of thought, which you then put into a normal LLM, can be quite a good way to improve its performance. And then if you want to play with this, there's the Hugging Face chat interface. You can select the distilled R1 and just play with it, just talk to it and see what it does. And also there's this idea of thinking in latent space, so making this whole thing more efficient by not doing the decoding step, which is really interesting and worth a read if you're interested. So just to say, prompting's really hard. There's so many things to consider and so many things at play that it's really hard to make an effective prompt. And we've just seen that the effective context that you've got to work with might not actually be that big. But that being said, there are a few good prompting guides. I like Anthropic's and OpenAI's are kind of the two big ones that I would recommend having a look at, and they will walk you through how to think about making a prompt and how to do it. And always remember that in-context learning is just incredibly powerful. If you can present some relevant examples and patterns directly in the prompt, the model will do much better at whatever it is that you're trying to get it to do. And that goes for showing it what format you want things in and showing it how to reason as well. And then just some general advice for prompt engineering is just it is a machine learning problem. So have a training set that you optimize your prompt in and a validation set where you test to make sure that you've not overfit to your training set. Don't just optimize this on one paper and get it to work really well for that paper and then it falls over on everything else. And with that in mind, you can actually automate this to an extent. So there's a couple of tools here which are displayed without kind of warranty. I've not had much success getting this to work myself, but your mileage may vary. You may be able to get your model to do a really good job with one of these tools, automatically generating a prompt for you. So we're now getting towards having something useful out, but we first of all have to decode the output of the LLM. And this is what happens so the LLM generates a probability for all the tokens, and then we need to pick one. And there's a few ways to do it. We could just do greedy decoding, where we take the one and only most likely token, and we just go with that. But by far the most common is a temperature-based decoding, where we directly sample the whole distribution, but with a temperature that controls the flatness. So this is the second equation, which is softmax with a temperature. And what's happening is we're basically smoothing out this distribution. So we're trying to complete the cat sat on the, and the most likely thing is Matt. But if we turn the temperature up, the distribution flattens out and we're sampling from this distribution. So we end up with about a 15% chance of saying the cat sat on the committee. And this temperature parameter controls how inventive the LLM can be. And then just to mention two variations on a theme, top K and top P, take a different subset of tokens and then renormalize and sample from them. They're very similar but slightly different, but you might come across those terms if you look into API documentation, for example. And so all of this decoding is usually unconstrained. So you just are looking at the temperature distribution and saying, okay, we're going to sample this token. And then you have to make your prompt so good that the token that is correct is guaranteed, basically, to be the right one, the most likely one, sorry. But if you know what you want, you can do much better. So you can constrain the generation in that case. So this very contrived example, I'm trying to generate an ID, and I'm telling the model it must be a number. But the model's read the whole internet, and when it saw IDs on the internet, they started with ID colon. So there's a non-negligible chance that when we try to generate the completion for this, it's going to start with ID colon and then whatever else. But we can constrain it with a regular expression and say, I only want numbers, I only want digits. So ignore all these other things that you think are likely and just sample from the ones that fit my regex. And this massively simplifies lots of things. So it guarantees that you can have valid JSON. You can give it a grammar, which is a way of specifying what's allowed in a sequence, which can guarantee valid C++ code, for example, or a valid sequence. And it reduces the amount of post-processing that you have to do on your outputs. It's starting to get some traction. So there's a couple of libraries here which I've used to great success. And there's some resources here if this is something you're interested in and want to learn about. In particular, this video from the guidance authors is really good at explaining how this all works, and I would recommend watching it if that's something you're interested in. So the last couple of slides, I want to talk about hallucination. So it's key in all this to remember that the model is just predicting the next token. And depending on what's going on, that token might not be the right one. So this can lead the LLM to generate things which are not true. And in particular, when we're doing chain of thought, it can lead to faulty reasoning. So there's a really nice, fairly recent paper that defines a taxonomy of hallucinations. They define 6 different types that range from it mixed up the entities that it's talking about through to this is just complete made up nonsense. And they have this website where you can have a look at it and play with it. And the sorts of things it can do is this, these are both taken from their paper, is if you have some grounding references, you can compare the references to the output and identify where things have gone wrong. And the example they give is that Lionel Messi moved clubs, and so now he's not in Barcelona, he's in Miami. And this second thing is just totally made up. But so the best mitigation against hallucination right now is grounding. And that basically means feeding in known facts. So using RAG or tools or something to inject truth into the context and the generation. And then maybe doing some self-checking. So this paper is called Check Your Facts and Try Again. And it tries to do exactly that, just fact check itself and regenerate if needed. So that's actually all we've got time for. It's been a real whistle-stop tour of LLMs, and I hope it's been useful. This has been deliberately background information. The idea being that you're going to see some really cool applications in the upcoming 4 talks. The key things that I wanted to get across are that LLMs are just a really simple architecture where the scale has been turned up to 11 and just made really big. And you just throw in loads of compute time and these things start to get really good at stuff. And you'll see lots of exciting applications coming up. So we've got dataset curation with Melanie is the next one. And we've got summary generation with Matthias, biochatter with Sebastian, and patient-derived cancer models from the cancer models team, all of which are really, really cool, and go and register for them because they're going to be really good. So with that, we've got a few minutes to take any questions.
Thanks, Andrew, for the webinar today, and thanks everyone for joining in. So we have had quite a few questions around parameters that you define in LLMs, tokenization, and reward, quality control, and LLM efficiency. So I think I'll start with the tokenization one. So the questions were around what's the best strategy for making the tokens better?
So it depends which model you're going to use. So if you're going to use an open source model, you kind of have some control over this. So you can add things to the tokenizer, and then you can update the embedding weights and fine tune it to understand those new tokens. So theoretically, you could add every single gene name for humans and then fine tune on a bunch of text, and those gene names would be their own thing. But in reality, a lot of us are probably not going to be doing that. We're going to be using an API, and you just have to trust that OpenAI are on top of this and that they listen to feedback and will figure this out, because you don't have any kind of control over it. So that's one of the downsides of using commercial models, is you cede control of pretty much everything in exchange for a really powerful model. To be clear, they're obviously miles ahead of things that are open source at the moment. So the short answer is, I think you could do it if you're doing open source things. Maybe for smaller models, it's something sensible. But if you're using anything remotely hosted, then you're out of luck, basically.
And for parameters, how do you define parameter? Essentially, what constitutes a parameter?
Yeah, so when I talked about the self-attention mechanism, those 3 matrices, Q, K, and V, are matrices. So every number in that matrix is a parameter. There would be, so they project from the vocabulary size, so like 200,000, down to the hidden dimension size, which might be 768. So whatever that number is the number of parameters in that little bit of the network. And it is literally numbers. So if I say a model has 175 billion parameters, there are 175 individual numbers which are being multiplied together in some way inside it that do the modeling that we're trying to do.
Now we come to the reward. So when you are tuning a model, how do you define what reward means for the model?
So where in human feedback, reward is basically which one does the human prefer, and that is a subjective measurement. You would hopefully tell the raters what to look for, but then it's just a straightforward classification A or B, which one is preferred, and the reward model learns that. So you feed it a pair of generations, and it says, I think B was the best in this case. And then when you're training against the model is producing pairs of generations, and it either gets a positive reward if it produces the one that's preferred, or a negative reward if it doesn't. That's propagated back through the weights to steer it in the direction of always producing the preferred one. And this is where that reward hacking idea comes from, because it can figure out a way to cheat the system basically and always get the reward without actually doing what you want.
Great. And I think the next question about quality control is somewhat related to this one. So in reinforcement learning, what quality control measures are in place to ensure reliability on human feedback?
Probably not many, to be honest. So what projects I'm aware of have aimed for is the biggest possible set. So if you were doing this in other fields, you would have some overlap and you would look at inter-rater agreement and stuff like that. But if you just want the maximum possible coverage, you will have one rater per pair and there will be no quality control, and you just rely on the law of large numbers, basically meaning that hopefully any bias that these people have will get washed out somewhere. Um, Other than that, I don't think there really is much quality control in that. You just have to train your raters well and then hope that they follow the training and aren't having some other bias that gets surfaced.
Thanks, Andrew. If you could take one last question. So is
Yep.
running challenges with LLMs. So in early years or even now, someone has asked, why do LLMs have difficulty with mathematical concepts?
So this is basically tokenization is a large part of it. So they have to be able to tokenize the maths problem in such a way that the tokens they're working on correspond back to the mathematical entities. So if you've got a few digits in numbers, then they'll probably end up in two tokens, and then it starts to get very confusing and muddy what exactly it's supposed to be doing. So there are whole data sets that try to see if the model can do this. So there's a benchmark called GSM-8K, which is kind of word problems in mathematics to see if the LLM can do maths, but maybe just not with numerals. Um, so I think it comes back to that problem of the tokenization can go a bit strange with numbers, and then it's loading more things onto the attention mechanism to try and handle. Modern models can pretty much do maths now. It's more of a problem for small models and older models.